Okay, it could be done that way. You use this very same concept. So, all right, for the beam, you will need to exercise 1 degree of freedom at a time. To exercise 1 degree of freedom at a time, so I'm gonna start with the U1. Okay, if I want to exercise the U1, I push the beam upward at that end, keeping the rotation at that end 0. Okay, you cannot allow the rotation over here, over there, and displacement over there. So how the deformed shape is gonna look like if you exercise the first mode of deformation. So it's gonna end up like this. Alright, so here is the original configuration. Okay, this is the reference. Alright, and then you push it up by U1. And then we keep the rotation there and there to be 0. We don't allow the U3 to be non-zero, okay? Everything else is all 0, but just U1. And then what is the step? Yesterday, once I deform the bar by 1 unit, the U1, okay? The next thing I did,
Equilibrium.
I check the equilibrium. I find the relevant forces, and yesterday was just force, okay? But now today we're gonna have force and moments that is required to displace this up by U1. So, okay, I need to find F1. I need to find F2. Forgive me, I will end up with this lowercase f, okay? Whatsoever in the local coordinates, I will use the lowercase letter. And then once we get out to the global coordinates, then I use the uppercase. So right now you have the small f, f1, f2, f3, no, downward, no, and f4. Okay. So if I say like this, actually to make it proper, I should put the absolute sign like this. Okay, that means we're gonna take just the magnitude of this force, and this force is going downward. Because once we take it out, then you're gonna find that this one is the minus sign. All right? Okay. So doing it like this will be quite proper. Okay. So can you find these forces? Is it possible? So that is not difficult anyway. All right. So when you want to find this thing, okay, you first. Let's say you have the force equals to P applied to this system. And then this system is superimposed with another system. If you look at this system here, this is the planar equilibrium, okay? So 2D equilibrium, you have how many equations? Sigma moment, sigma force x, sigma force y. But what we are doing over here, we have nothing to do with the x equilibrium. So we have just 2 equilibrium remaining, just 2. 2 equilibriums. How many unknowns do we have? We don't have any idea about the force here, force there, and moment. Okay, all right. So we end up with 4 unknowns. 4 unknowns to equilibrium equation, so you cannot solve. All right. So to solve it out, you got to release 2 things off. Okay, and then I selected this force and the moment at the left hand side here. All right. And then we have only just 2 unknowns over here. So one unknown being the reaction force and another will be the moment. Alright, these 2 adds up. You will end up with this shape. Okay? but we need to find the right proportion of the P and the M such that you end up with this picture. Okay, so first of all, this P is gonna produce this deformed shape. Okay, this deformed shape, you will have the deformation, let's call the delta superscript P. Okay, you push by the force P upward, then you end up with the deflection upward. Also, you have the rotation, let's call it theta P. Okay. In contrast, if you apply the moment at the tip like this, so this moment will produce this deformation, this deformed shape. Okay. At the end, at the support, you have zero slope, and then, okay, over here, delta superscript M and theta superscript M. We just note that delta P and delta M, they are in the opposite sign. Theta P and theta M, again, opposite sign. Alright? So I will not focus too much in the sign convention of the scheme that we use to come up for this derivation. I'm not going to use the moment area theorem, but I know that this is like long time ago. You may not still remember. Okay. But what you have over here, if you apply force P, then you have the P acting downward as the reaction. And then to keep this in equilibrium, you will have P multiplied by L if the length of this beam is L, and you have the E as the material properties, and you have the I as the secondary moment of inertia. The EI adds up to the rigidity of the cross section. Okay, so you end up with the PL. With that PL, okay, if the EI or the cross sectional properties is constant, alright? If the EI is constant, then you can construct, first of all, you can construct bending moment diagram. So your BMD is gonna look like this triangle for this case. And then you remember that, okay, you have the PL, and when you want to find angle, you want to find deformation, deflections, you use not the BMD, but you use the BMD over EI. Okay? So you have the moment divided by EI. Why PL over EI? That's why moment over EI. I try to go through the fundamentals a little bit, alright? So if you forgot this already, or if maybe you haven't learned about this, okay, we're gonna spend just a little bit of time understanding, okay, what is. So, you're aware, okay, your curvature. Curvature is represented by the phi. Curvature is what? Curvature is the change of the angle, okay, over the x. So you have a beam. The beam has maybe the deformed shape just like this. So you have the theta that is changing, okay, along the way. Okay, the change of angle over the dx, if this is your x, so you will have the change of angle over dx, okay? Let's say it is actually the derivative of theta, alright? So derivative of angle with respect to x, you end up with the curvature. This curvature will constitute with the EI, you end up with the moment di